Okay, in this program, we're looking to optimize uh, the job of creating these 12 rectangular pens. Each pen needs to have an area of 200 square feet. And to kind of share some sides and walls together, the individual has decided, hey, I want to use this layout. So that way, some of the pens, like this first one here, it has two walls that are its own, and then another wall is shared with two other pens. You can see this middle wall pen here is actually sharing three walls, whereas some of these internal ones here, the two in the middle, are actually getting all their walls, except for the one they share, from the ones on the outside. So that would reduce the amount of material used. So how are you going to get to the middle pins? I don't know. We're going to have to probably have gates on each of them end of it anyway, so we'll have gates from one pin to another. Maybe not optimal, but or maybe this is something where we're going to walk across the top and lower the materials inside. I don't know. Uh, but there would be ways to do that. You'd have to have that anyway, whether you had separate pins or 12 completely separate pins. So a farmer wants to make 12 rectangular pins, each with an area of 200 square feet. And so the question we ask here is what dimensions should be used for each pen to minimize the amount of fencing. And then second question, once we've figured that out, what dimensions, how much fencing is needed to fence all 12 of these pens. And you can go back and work it out for an individual pen and then multiply that result by 12 and kind of compare it. And you'll see that we are in fact saving, definitely saving on material used here. So as we approach this problem here, we have really two choices. We could decide to let the whole side be X and the whole side be Y, in which case we could use the relationship area is X times Y would be all 12 of these 200 square foot pens, which would be 2,400. Or what I did is I chose X to be the length of an individual pen. Length of an individual pen, and the same thing for Y, specifically because I do want my dimensions in my final answer here. So what we realize is that those X's and Y's are for every one of those dimensions of every one of those individual pens. And so what we need to come up with is our function to minimize, which would be the amount of material, or in a sense, the kind of perimeter. It's not really perimeter because we have inside pieces as well, but we can call it that. But first off, what we know for sure is that area is X times Y for the individual pen, and that has to be 200 square feet. Now that does not contain the quantity we want to optimize, so that's not our primary equation. Rather, that's an auxiliary equation. That's an extra equation. And that extra equation will allow us to solve for one of the variables there. So I might decide to solve for y, so I get y equals 200 over x. And remember, it's that auxiliary equation that can help me get constraints, practical constraints on the problem. Since y is 200 over x, about all we can say here is x has to be greater than 0. But we also realize that there is going to be some reasonable limit in here beyond which, if you make x 300 feet long, and then y would be 200 over 3 feet, be 2/3 of a foot wide, that's probably not the optimal way to go. So when x gets too big, it's going to kind of naturally defeat this problem. So we don't have an upper limit, but the understanding is when x gets really, really big, if you're using almost all of it to make a length, then you're using way too much material, and definitely far from optimal. So now we go to, well, what about our, how much material are we using? So that's our perimeter. Well, if we look here, we have x 4 times along this length. That happens again here, and again here, and again here. It happens 4 times. So x shows up 16 times in the material list. The y variables, we have 3, and then another row of 3, 3, 3, and 3. Y shows up 15 times. And so we have our relationship now that contains the quantity that we want to optimize. P equals 16x plus 15y. And so as we continue through here now, we can start simplifying. We know that y is equal to 200 over x. So I can put that in there. 200 over, that should be 200 over x there. My pen missed a little piece there. Okay, and then we can simplify that though, because 15 times 200 is going to be 3,000, and 3,000 over x can be written as 3,000 x to the minus 1. 3,000 x to the minus 1. And so now I did that as x to the minus 1 because now that we've found our primary equation here, P, we can now differentiate to try to optimize it. We can now differentiate to try to optimize. So we find P prime. Derivative of 16x is just 16. Derivative of 3,000 x to the minus 1, looks like I have another little typo here, is minus 3,000 x to the minus second power. Minus 3,000 x to the minus second power. Okay, we then continue here, rewriting that is P prime equals 16 minus 3,000 over x to the second power, the negative second. And we want to solve that equation for when is it 0, when is it undefined. So when is P prime 0? So 0 equals 16 minus 3,000 over x squared. Here we can multiply both sides by x squared. That would give me 16x squared minus 3,000 equals 0. And then solve for x squared. So bring the 3,000 over, divide by 16, and then take the square root. So we get x equals square root of 3,000 over 16. That is roughly 13.69 feet. And then we also need to ask a question, when is P prime undefined? When is P prime undefined? P prime is undefined at x equals 0, but we already know based on our constraints that that actually isn't really going to matter. That's not going to matter because we're dealing only with being greater than 0. So the only value of interest here is this 13.69. And so we want to use that 13.69 to figure out, okay, well, what's our y value? But hold on. Before we can do that, we do have to answer this question. Is that actually a minimum value? Are we actually minimizing the amount of material here? To know if we're minimizing, we need to look at the derivative above and below 13.69. Is it decreasing? Is it negative before we get to 13.69? Is it positive afterwards? So if you go back to the derivative here, you can plug in like P prime of 1. That's going to be 16 minus 3,000 divided by 1. Definitely negative. And then we need something bigger. So, I don't know, put like 100 in. Put something like 100 in. That would be 3,000 divided by 100 squared. 100 squared would be 10,000. 3,000 over 10,000 is 0.3. 16 minus 0.3. Yep, definitely positive. And that also kind of lines up with our idea. If we let x get ridiculously big, the amount of material should be absurd. And that's what our model is laying out. So yes, this really is a minimum amount of material. So we can now say, okay, now we need the dimensions. We know x is 13.69. So what's y? Well, we know that y is 200 over x. Y is 200 over x. And so we can go ahead and plug that in. Plug into 13.69. We'll get y is 14.61. 14.61. So it's almost a square, but not quite. About a foot difference between the one side and the other. And then there is one other question we're asked, and that is, how much fencing do we need? Well, that's where we can go back into our fencing equation here, 16 plus 3,000 over x. Plug in our x answer of 13.69. And when we do, we'll get our total amount of fencing needed is 438.2 feet of fencing. 438.2 feet of fencing. Okay, there's one final piece to this question we want to ask, and then we're going to break this and resume this problem in a second video. And that is, if the fencing cost us $4 per foot, what's the cost for this optimal situation? Well, we just take our 438, not dollars, 438 feet, 0.2 feet, times our $4, and that would give us our overall cost of $1,752.80 is what it would cost us to make these pens. $1,752.80 to manufacture our pens. Okay, so pretty long problem. We're going to look at this from a second point of view in a moment with our decision for how to make these things. And we're going to take a look at that and kind of compare it maybe a little bit to what we've just found.